Hello. Hi, everyone. Today I'm going to talk about our journey so far to try to Kubernetize big data and ML workload at Uber. As you know, Uber has actually become a pretty fast-growing and a big company. We went IPO this year, and the growth is pretty big. We have like 15 billion trips. So far, if you remember last year when we had the talk, we had like 10 billion trips. So just like 1 year, like we recorded like 5 billion trips. And we do like 15 million trips per day. And we're a global company, different compared to like our competitor. We are like a more global company. We're in 6 continents and 65 countries and 700 cities. We have like 100 million active monthly users. And we're serving almost close to 4 million active drivers. So big data and ML is very important for a company like Uber, because that's kind of how we can potentially become profitable in the future. So we are like using big data and ML in all different areas like Uber Eats, ETAs, self-driving cars, and like lots of use cases. I'm going to quickly go through a couple of them. For example, one example is ETA. As you know, whenever you open Uber app, it's going to tell you what's the pickup ETA, what's the arrival ETA. So those ETAs are very important, not only from customer experience perspective, also from like a pricing perspective. So we are using ML models to predict the route-based ETA errors and use that to compensate the errors. So that's actually very important for Uber business. And the next one is like fundamental to core of the Uber business is how we matching drivers and riders. So in that area, there are lots of ML algorithms as well. Next, we also have a new business line. Not exactly new, but it's like fast-growing business line, which is Uber Eats. We use lots of ML models for ranking of restaurants and the dishes, delivery times, as well as searching ranking. So like every time when you open the Eats homepage, there's like more than hundreds of ML models get called to render the page. Now, of course, we also have a self-driving car units. As you know, like that's ML models is fundamental to lots of aspects of the self-driving car, like perception and also 3D mapping. So let me quickly go through, introduce the Uber's big data stack. On the right side, we have a tiered data lake. Basically, we have hot storage like HDFS and warm HDFS, as well as archived. And in front of that, we have some in-memory database. And then on the left side, we have lots of events, basically from mobile app, microservice, database, and third-party events. And we basically use Kafka to feed all those into our data lakes. And then we have a compute fabric. Today, it's a combination of Yarn plus Peloton on Mesos. If you're interested in about that, you can go back to our talk last year. So, but our plan is kind of to go to unify all those into become a Kubernetes plus Peloton. Then on top of the computer fabric, we have our data processing engines, which including both streaming as well as batch processing. We're using Flink, Spark, and Tez. Then on top of that, we have our query engines, which is like real-time engines like AntennaX, as well as Hive, Presto. Then on top of the query engines, we have our data analytic tools like Piper, which is Uber's version of Airflow, and dashboards, ad hoc queries, and BI tools. So as you can see, compute fabric is very important to big data, because that's basically the core of the engine where all the big data is running. Now, let's move on to the next one is ML. So in ML at Uber, we have a ML platform called Macangela. But we're basically trying to platformize the whole ML workflows within Uber, including data preparation, phototyping, training, as well as inference. So the idea is like, every ML engineers can just do a couple clicks, and then they can specify what's the data sets and what's the models they want to use, and then what's the algorithm they're going to use, and then we're going to train all the models, deploy the models, everything in an automatic way. In this system, actually, as you can see, the compute is also like very fundamental to that, not only from analytics training perspective, but as well as like inference, real-time prediction. Then there's also like, we have to support different training engines like TensorFlow, PyTorch, XGBoost, Spark ML. So now the question is, why Kubernetes? We can say, okay, you can use Yarn or Mesos plus Peloton, that could serve the needs, but why do we move to Kubernetes? So there's, first important thing is there are lots of features and extensions in Kubernetes for mixed workload. So Kubernetes, when it's designed, it was for mixed workload, right? So basically it supports like deployment, pod, stateful set, batch jobs, as well as daemon set. And most importantly, the growing community. So everybody here can see like how many attendees for KubeCon. It's growing every year. And wide adoption of wide adoption as well as native integrations from open source projects like Spark. Also like cloud native support and flexible extension models. Now the question is, can we just use Kubernetes as is to replace Yarn and replace Mesos? The answer is not really, right? There are a couple like missing pieces in today's Kubernetes, which is not as popular as a big data platform as Yarn today in large scale production like Uber. There's a couple gaps like elastic resource sharing. Basically, Kubernetes don't have a Yarn queue concept. So you have like namespace, you have quota, but those are static. If you specify, assign some quota to one organization, if that organization is not using that quota, you cannot really use that quota for other people. Now, also like for Gantt sharing for ML workloads, and support like batch and stateless workload collocation. So this is not only just like put them together, but also make sure the batch workload is not interfering the real-time workload. Or real-time microservice workload. Then also like we want to like, if we want to replace Yarn, then we have to match the high throughput of Yarn, which is like more than 1K per second pod launch, what we observed today in Uber. Now there's other like dynamic pod allocation, which is important for Uber because we don't really use DNS, because that's not going to scale to like 10,000 nodes clusters or more. Instead, we have something called Uber naming service, which is very similar to like BNS from Borg. So for those to work, we actually have to like, for every container, you have to like dynamic allocate pods. So before I go to the more details, let me quickly introduce like Peloton. So we had talked about Peloton last year. So it is kind of a unified resource schedule designed for mixed workload, which has integrations on Mesos, and also we are building the integrations with Kubernetes as well. But the current way, actually that was in a talk on Tuesday, is basically just have Kubernetes as a plugin to Peloton without touching too much of the high-level architecture of Peloton. So this has like one limitation, which is we still have to build each driver for Peloton. It's okay for like microservices because within Uber we have our own deployment systems which can use Peloton API. And then for big data and ML, it's kind of a challenge. For example, we actually have a Spark driver for Peloton. So that's what we have in production today. But we have to maintain like different versions for every Spark. We support Spark 2.1, 2.3, 2.4. It's like huge maintenance cost. Now, if we can move basically, if we can move to support native Kubernetes API, then that can unlock lots of use cases and also can reduce our maintenance overhead. And also, with Peloton as a plugin, we can also support elastic resource sharing, Gantt scheduling, and high throughput with some performance tunings of the Kubernetes system. So let me quickly introduce a concept called a hierarchical resource pool. So the idea is that it's very similar to Yarn queue. The idea is that different organizations will have a resource pool, and then you can assign 3 parameters to each resource pool. One is reservation, one is limit, another is share. And then basically reservation is like the minimum guarantee of how much resource you can use, and limit is what's the max. And share is like the proportion of extra resource you can use if the cluster is idle. And then we calculate this entitlement, which is somewhere in between reservation and limit. In this Peloton on Kubernetes world, we actually model each resource pool as a Kubernetes CRD. So basically, you can do kubectl, apply a resource pool setting like a resource pool marketplace, and then you get that resource pool which specify, what's the reservation for CPU for each of the resource dimension, like CPU and memory. So this is how the Peloton scheduler is designed. The idea is we basically reuse all the resource pool code, all the port scheduler, placement engines, preemptors for same methods, but instead using methods underneath, we actually gonna basically watch the resource pool to populate the resource pool tree, and then we have a port watcher to watch all the port creations, which like all the unbanded ports, and in queue to each individual resource pool queue. So basically each resource pool has a pending queue, and then in the background we calculate what's the entitlement for each resource pool, and then admit them to the ready queue. So after they're in the ready queue, we have the placement engine to dequeue all those ready ports, and then bind them to the Solo API server, and then it's going to launch the Solo Kubernetes. And then on the other side, we also have a node watcher, which watches all the node informations and put them in a node cache. So let me quickly give an example of elastic resource pool. So for example, in this example, we have 3 resource pools. Each of them has a reservation of 20 units, and then have a limit of 100. So initially, for example, resource pool 1 only have a demand of 20 or of 10. So basically, there's no port launched through this resource pool, and then we're actually going to let resource pool 2 and resource pool 3 to use the additional resource. So basically, because their demand is much higher, they are have demand of 80, and then each of them will get 40 units of resource. Now, then next time cycle, we could launch more ports in resource pool 1. So at that moment, and we're going to recalculate the entitlement, and then we're going to figure out okay, now each resource pool should kind of deserve 33 allocations, and then we're going to preempt back the ports in resource pool 2 and resource pool 3, and give those resources to resource pool 1. So next, Mayank is going to talk more about Spark and other applications on top of Kubernetes Peloton.
Hey guys, so now we have Peloton running on top of Kubernetes. So let's talk about how we are running Spark and other frameworks on top of it. Let's talk about Spark first. So we have Spark running differently in different clusters. We have some Spark running on Yarn, some Spark running on Mesos, and some Spark running on, we started to move Spark on Peloton as well. So there are different challenges for each of these. For running on Yarn, currently we don't have Docker support in Uber. We have it in upstream, we haven't used it yet. And we have a lack of big container set support also for Yarn in Uber. We have challenges running on Mesos. Mesos does not have elastic resource sharing, as we talked about it. And then the bigger problem is Spark job registered as a framework, which is a scalability bottleneck, right? So you cannot run 200 to 300 Spark jobs together in Mesos. So then that's the reason we came up with the Peloton. So right now Spark running on Peloton, but we have to support all these drivers, which is a bigger cost because you change APIs in Spark, they are changing APIs left and right, you have to keep on maintaining it, fix bugs for each version, because once you have such a big organization, you have different versions running every time, right? So this is a big cost. We are still in production from 2 years, Spark, and there are 6+ production clusters running Spark. So that's the reason we thought, okay, this is not the scalable, so let's do something else. And that's why we wanted to run Spark on Kubernetes. So the multiple reasons running Spark on Kubernetes, right? So Kubernetes is becoming the de facto for AI and ML workloads. So we wanted to consolidate everything together. It's very expensive to maintain all these custom drivers. So we wanted to unify all these Spark drivers and ML drivers and ML frameworks together into one resource scheduler. And that gives us two things. One, we will not have this cluster fragmentation. So that means we would not, so let's say if one cluster is free and another is busy, we can use the workloads to, I mean, if it is one cluster, we can use the resources appropriately. And secondly, we can now prioritize all these workloads. If it's running into one compute platform, you don't need to have this global priority. You can have your local priority for each organizations, and then that can be prioritized across your workloads. So these are the advantages you want to use for one resource scheduler. And definitely we wanted to leverage the growing community. We see there is a lot of momentum in Kubernetes and on top of Kubernetes all the frameworks, right? So we wanted to use all of that. We can use out of the shelf all these distributed TensorFlow, Spark, Flink, all these drivers which is already working for Flink, we can just use them, right? We don't need to have the support cost. So these are some of the reasons we wanted to go Spark on Kubernetes. So this is, we are running Spark on Kubernetes right now. We have Peloton scheduler, so somebody submit a Spark submit job to API server. Peloton scheduler takes that job, put it into its hierarchical resource queue, and then we go admitted it based on admission control, and then it watches the nodes and then bind the pod. Then Spark driver go and launch that in some in kubelet. Then the Spark driver, then the normal Spark scheduler runs in Spark driver, which go and talk to API server, get the executors. Then those executors again go to Peloton as a scheduler, and then go admission control, scheduler, and all that, right? And then they get launched into another kubelet for Spark executor. And then Peloton scheduler can do all kind of preemptions based on the quota management and all that other stuff, right? So this is how this Spark is running on Kubernetes right now. So we have this Peloton scheduler which can do all that. So there are certain challenges running Spark on Kubernetes right now, and we have solved some of those. So lack of elastic resource sharing right now in Kubernetes, so which we are complementing with Peloton resource scheduler, resource pools. Second, there is no support of global, we don't want to, so in batch workloads, the global priority is very hard. You have many organizations which is running, and you don't have to have a global priority. Kubernetes right now works on a global priority. You need to have all workloads to be prioritized into single scale, which is not possible for batch. So you probably want to have each organization has their own priorities. So this is how we enable it through resource pools. Currently, Spark does not support dynamic resource allocation because of there is no external shuffle service in Spark for Kubernetes right now. So we are solving it through, we already wrote remote Spark shuffle service, which we'll talk about a little further. And then there is not a support of secure HDFS. So we are passing Kerberos tokens through security, Kubernetes secrets. So this is how we are overcoming all these challenges for Spark on Kubernetes right now. So let's talk about how, just overview how this local shuffle works. So right now what happens is the Spark mapper and reducers runs. Mappers write to their local disks. Then they generate, generally we have this SSD machines. We are on for compute machines are SSD machines. So all these local shuffle or the external shuffle write all this data into the local disk. This is how this is being laid out on the disk is you have index files and you have data files, and local shuffle mapper write to the local shuffle service, and then they are being written into these index file and the data files. And these each partition are laid out. When reducer comes, a reducer goes and talks to each local shuffle service, finds out which partition it needs to find out. It goes and tells the local shuffle service that, okay, I want these partitions. And then it goes, merge them, and then give it to the iterator for the reducer, right? This is how your local shuffle works. There are certain challenges of having this local shuffle service right now. First, if you are using SSD machines and if you are using lot of writes to the disk, your SSD got weird out. So we have our data centers which we used to run the SSD for 3 years. Those SSD got weird out in 6 months. right? So all the disks were bad within 6 months because we write so much data or shuffle data onto the disk. There is something called DWPD in each SSD, which is called disk write per day. And if you exceed that per day, then your life of your SSD goes down. And this is what is happening in our data centers too. So that's when we thought, okay, we need to write something which, because you can have better SSDs, but there is those are not good in terms, in terms of your economics, right? So you don't want to put those higher SSDs. So second problem is reliability. Very often you see that your job got killed because somebody else wrote a lot of data onto your disk. So this is like noisy neighbor issue, right? So people write a lot of data, and then certain jobs get failed. This is like every day we have like 3,000 jobs failed in our data center. In Yarn cluster, 3,000 jobs fails because of this issue. For the Kubernetes, we don't have dynamic allocation and the collocation also. So we wanted to write unified scheduler, so we wanted to collocate stateless and batch together. However, we have so much data written for the batch jobs into the local disk, the disk utilization becomes 100%. And because of that, all the stateless services running on that machine gets unresponsive. Because you are writing so much data, your load average on the machine is very high. And because of that, you can't even go and do SSH on those machines. So the stateless services, which are very, very latency sensitive, gets like very much blocked in terms of throughput. So we can't do collocation on the same machine if you're writing so much data. So this is what we have thought, maybe this is one of the reasons we should write a remote shuffle service. So this is how we did remote shuffle. We have so there is something called Shuffle Manager. Shuffle Manager, it's a part of your Spark today. However, you can plug in different storage into your Shuffle Manager. You can say local, you can say remote, you can say NFS, you can say HDFS. And you can write your own Shuffle Manager for that today. But we did these experiments with those Shuffle Managers. We wrote HDFS Shuffle Manager, we wrote NFS Shuffle Manager, because we wanted to see, instead of writing to local, we can write remote. But we did that, and the experiments were like 2x or 3x slower, even on NFS, even on HDFS, right? Because there is a lot of data which people, a lot of small files with these host or these mapper tasks, right, which cannot get, so the closing, opening file going on network causes so much issues and so much latencies. Because of that, the latency of the whole job becomes 2x or 3x slower. So we took a step back, and what we did was, we changed the little bit paradigm for Spark Shuffle right now. What we did was, so all the Shuffle Manager goes, and so we have a cluster of shuffle machines. All the Shuffle Manager finds out which partition and I can write to which shuffle server. And then these shuffle partitions, all the mappers of same partition will go to one server. And the server will write into the local SSD sequentially. So because of that, reducer will go directly to one server and fetch all the records into one shot. It doesn't need to go to each machine and find out where is the partitions are, merge them together and all that. So it doesn't need to do all that. It's all there, go to one server and fetch the file. And after doing that, and these are all streaming, so mappers are streaming to remote shuffle, and reducers are streaming from remote shuffle to the local. After doing that, we are actually on par performance with the local shuffle. So we are doing remote, but the performance is pretty much the same what we used to get from external shuffle. So remote shuffle we are doing last 3 months. All these Yarn and Peloton workloads are running on top of it. Currently, thousands of applications running. Job latencies are on par with external shuffle right now. And we are actively enhancing that. Working towards onboarding all Spark workloads onto remote shuffle, and we are trying to open source it soon. So let's talk about GPU and deep learnings, right? So as Min said, we have a lot of use cases which are using GPUs and deep learning today in our compute stack. We have like self-driving vehicles, we have trip forecasting, fraud detection, and many, many more deep learning use cases which are coming up on GPUs. There are certain challenges when running distributed TensorFlow right now. We don't have elastic GPU resource management, so that is one of the issues which we are complementing with Peloton. We don't have locality and network-aware placement. Task discovery is an issue. Gang scheduling, which is a challenge right now. We are trying to solve it through Peloton, and as well as the failure handling if one of the tasks goes down, right? Gang scheduling, let's talk about a little bit on the gang scheduling piece. A subset of the task in job can be specified as a gang, right? You can say, these are the tasks run as a gang. So what are the primitives which we need to follow? They have to be admitted as a gang, scheduled as a gang, preempted as a gang, and killed as a gang, right? So these are the primitives which are missing, and which Peloton have it. We have that in production on Peloton and Mesos, and we are trying to do it through pod groups into Kubernetes. Gang tasks are, what we do is we take as a gang, we admit, we do all the resource sharing, all the quota management, we admit, based on that we do admit as a gang, and we bind or place as a gang. And then if we wanted to preempt any of the tasks because of the priorities or cluster is busy and whatnot, we do preempt all the gang together. Similarly, if something fails, we make sure that the whole gang is being killed, right? So this is how we added the gang primitives. So this is how we run distributed TensorFlow right now on Kubernetes. So Michelangelo is our deep learning service, which runs and talks to API server, create the pod. And similarly, Peloton takes that pod, do admission control, place it, and then once it is placed, it plays in through parameter server and this worker executor. And every pod runs two containers, with the parameter server container and the Michelangelo container, because that's the service which we use. And then they go and discover each other through API server, right? And then they get launched and then run as a gang. So this is how we currently run a distributed TensorFlow on Kubernetes. So let's talk about a little bit of workload co-location. So why we wanted to why we want to co-locate workloads? This is a bigger problem for efficiency, right? If we run stateless servers separate than the batch servers, then you cannot use all the resources how you should be using. We are aiming to use 20 to 25% of the resources if we can work them or run them together. And 20 to 25% resources is, if you're talking about Uber's fleet, it's like huge amount of money, right? So, and we can save 20 to 25% of money or servers if we co-locate them. The challenges are, if you wanted to co-locate them on the same machine, the disk I/O, which I just talked about, network on the machine, CPU caches, and the memory oversubscription. So, right, so if you're running everything together, then these are the challenges which happens today. So what we thought is it's hard to solve this. These are the problems onto same machine. So what we thought was, okay, but we can solve it on the same cluster. So we created something called dynamic partition into our cluster, which is you have stateless partition and you have batch partition. So you have two different partitions. You oversubscribe all these physical resources on each partition, and then you move machines if needed. So as I said, you have this cluster where you have stateless partitions, you have these batch partitions, and all these partitions are running, the stateless partitions are running stateless services, batch partitions are running batch jobs, and then we are measuring the hotness of each partition. So you see 40% utilization, 40 to 50%, and 50 to 60%, right? So we oversubscribe the resources on each partition. This is how you save money. You pack each services and each job, more job together, and then you measure if something is getting impacted, you move machines based on that. So this is how we do, right? So we measure the partition, and then the nodes which are least loaded, we move them into different partition based on the hotness of each partition. So if your partition is like 70 or 60% hot, we move machines from the other partitions to this partition. By that we can easy up this this partition, and services and other jobs are not getting impacted. There is an assumption here. We say services are higher priorities, or the stateless services which are higher priorities than some of the batch jobs. So this is the underlying assumption which we take in our clusters. So this is how it works. We have something called node agent, which runs in each node, which measures what is the CPU length, what is the CPU load, and all different CPU matrices for each node, and then send it to something called node advisor. Node advisor goes and finds out from all the nodes what are the load and the inference of services on these nodes to each other are. It finds out that, and then it gets that information to the Peloton scheduler. Now, Peloton scheduler will take decisions based on if the partition is hot, if the node is hot, or the services is hot. Based on these three parameters, it takes decision which machines we need to move from which partition. By that, we don't impact these services which are running or the jobs which are running. And we want to do it proactively because we don't want to, because if you do reactive, the service is already impacted. So we try to measure the whole partition along with the node as well as the service. So if we see the partition is growing in terms of hotness, we move machines to that partition. So for that, it seems easy. We have to do a lot of work to do that. We did load-aware placement. Load-aware placement because we have to do the load-aware placement because we don't want to cause churn into the system. Because it may happen that one machine is hot, and then you move service from that machine to another machine, and that machine is hot. So you always place into that partition based on the load on the machines. We have the scorers. We build the scorers for batch and stateless, which can find out what is the right machine at this point, which we can move. Virtual partition, we added partition within partitions because there were some batch jobs which are needed, which are more important. And the break glass, right? If there is a spikes into the unusual spikes in your services, then we can go break glass and then get all the machines from the batch with the assumption that the batch machines, some of the batch workloads are not as important as stateless, and give those machines to the stateless clusters. So this is how we are implementing this colocation. This right now it's implemented in Peloton, so it's pretty much orthogonal to Kubernetes or Mesos. So summary, Kubernetes is the future for big data and ML workloads based on the adoption. So we have done Peloton and K8 scheduler POC. We are already implementing all these batch features. Peloton on Mesos is in production, stateless and batch, and we are thinking how we migrate and looking for collaboration to enable Kubernetes for big data and ML workloads. That's all. Thanks.